Today we'll briefly talk about the definition of another algebraic construct. So this is called an algebra over a field F. Okay. So one can more generally define algebras over a commutative ring, but for now let's just restrict ourselves to algebras over fields. So what is an algebra? Well, it's the following. Let F be a field. So let's fix a field F. Okay, so an F algebra is an abelian group R, say R plus, together with a multiplication. So what is a multiplication? A multiplication is a map. It's a binary operation, if you wish. Let me just call it dot. So multiplication is a map R cross R to R, which takes a pair AB to A dot B. Okay, it's a binary operation, and so with a multiplication map and a scalar multiplication map. Okay, so what's a scalar multiplication map? This is a map from the field cross R to R, given a scalar alpha from the field and an element x from R. It maps it to some element of R. Okay, so which is alpha. Let me put a circle dot x. So I'm given two maps at the moment. I will tell you what the axioms are, but at the moment I'm just calling these maps by these names: a multiplication map and a scalar multiplication map, such that the following axioms hold. So recall, there are three things. It's an abelian group. It's got a map like this, R cross R to R. It's got a map from F cross R to R. Okay, such that the following things are true. Number one, if you look at R with plus and the multiplication, then this is a ring. Okay, property 2. And if you look at R as an abelian group together with the scalar multiplication, this becomes a vector space over F. F vector space. Okay, so in some sense, therefore, it's a ring and a vector space, but the two operations sort of are compatible. And thirdly, the compatibility axiom, which says that if you scalar multiply a scalar alpha with a product of two elements of the ring, then this is the same as first scalar multiply A, then multiply by B in the ring, or multiply A with the scaled version of B. Okay, this should be true for all scalars from the field, for all elements AB from R. Okay, the third axiom is really the compatibility axiom. Okay, now what are examples? Because why is one studying this concept? Well, there are large number of very interesting examples. So here are two of them. So if F is the fixed field there, I've fixed F for now. I can look at the set R of n cross n matrices over the field. So this is all n cross n matrices over F. Okay, now observe what is the multiplication and scalar multiplication. So recall, this is, of course, it's a vector space over the field F. You just scalar multiply by multiplying every element of the matrix by the given scalar. This is also a ring. It's got a ring structure, just usual matrix multiplication. Okay, and the key point is that these two structures, the scalar multiplication and the multiplication, satisfy the compatibility axiom. Okay, this axiom is definitely true, because it just says if you take a product of two matrices and then multiply by a scalar on the outside, it's the same as you multiply the first matrix by that scalar and then multiply the two matrices together, or multiply the second matrix and multiply it by the first one. Okay, so this is, of course, just a well-known property for scaling and multiplication for matrices. Okay, number two is, well, you can take polynomial rings. You can take, so here this ring structure is not commutative, but here the F algebra Fx, which is all polynomials with coefficients in F, this is just the polynomials in X in one variable with f coefficients. So this is of course a ring. Again you have multiplication, but it's also got a vector space structure. You can multiply a polynomial by a given field element, and here these, it's easy to check again that the compatibility is true. Okay, so these are all examples of F-algebras. And so these three axioms of an F-algebra 1, 2 and 3 can also be written in a slightly different form. Okay, and so this is sort of an equivalent formulation, if you wish. So observe that if I am given an F-algebra, so so before I tell you what the formulation is, let's make some observations. If R is an F-algebra, okay, what does it mean? Well, it says the following. I know how to scalar multiply elements of R by elements from F. So consider the following map. Take a scalar alpha and map it to the ring has a special element, the multiplicative identity. You scalar multiply it by alpha. Okay, you can scale 1 by alpha. That gives you some ring element, right? So consider the map. Now, what sort of map is this? Let's call it phi. Consider phi defined like this. Then claim is that phi is actually a ring homomorphism. Phi is a ring homomorphism. That's property 1. Claim property 2 is that the image of this phi is actually contained inside the center of this ring R. Okay, so I claim here are two special properties, that phi is a ring homomorphism and its image is contained in the center of the ring R. Okay, so why is this true? Well, both are easy to check. Let's check the first property. For example, so if I have, so what is phi of alpha beta? By definition, it's alpha beta scalar multiplying 1. But how do you scalar multiply alpha beta with 1? Well, one way of doing this is to say, well, let's say it's alpha beta scalar multiplying 1 into 1. Okay, because the multiplicative identity is just 1 times itself. And now, so alpha beta is a scalar. So what I can say is that, but because of the vector space axiom, when I multiply, so maybe we'll do that in the next step just for clarity. So when I have alpha beta multiplying 1, this is just alpha scalar multiplying beta scalar multiplying 1, right? This is just the vector space axiom, if you wish. Okay, but what is this? This is alpha scalar multiplying. So beta scalar multiplying, I will write this as 1.1. Okay, now let's go here. This is alpha multiplying. Now let's use one of the axioms. This says this is beta times 1.1 is just the same as 1 multiplying beta dot 1. So this was the compatibility axiom. Okay, and now finally think of this as some ring element, this as some ring element, and alpha scalar multiplying that is the same as alpha multiplying the first element and that multiplied by the second element. Okay, and so this is exactly phi of alpha, phi of beta, which shows that it's one of the properties of the ring homomorphism. Okay, so again you have to check phi of alpha plus beta similarly. Okay, so so let me leave that as an exercise. So similarly check phi of alpha plus beta equals exercise. And the unit element of the field maps to the, this is the easy part, the identity of the ring. Okay, so now what this means, it's a ring homomorphism. Now why is the image inside the center? That's a second property. So let's check the image of phi. So what's the typical element of the image? It looks like alpha multiplying 1. Okay, let's take a typical element, alpha multiplying scalar multiplying 1. This is a typical element of the image. I claim that this element must be in the center. In other words, if I take this and multiply it by some ring element R Question is, what do I get? Well, what do I get? Again, by the compatibility axiom, alpha times 1 dot r is just alpha scalar multiplying 1 into r, okay, which is just alpha times r. Whereas if I multiply it in the other order, r times alpha 1, again the compatibility axiom says this is just, okay, but that's just alpha times r. Okay, therefore these two things are equal to each other. Okay, in other words, alpha scalar multiplying 1 commutes with the element r. Okay, so this means, okay, so what this means is that if you have an algebra, if you have an F algebra, then that comes from that you can define a map phi from the field F to the center of R. Okay, so this phi, the ring homomorphism from F to, okay, you can construct this. Okay, but in fact conversely, so actually this is giving such a map is equivalent to giving an F algebra structure. Conversely, if I have an F algebra or given such a map, conversely, if R is a ring, the ring homomorphism, then R is actually an F algebra. Okay, R becomes an F algebra via the following definition of scalar multiplication. Okay, what's the definition? Given any element alpha, how do I, and an element R of the ring, how do I compute alpha scalar multiplying R? I define it to be, I first apply this homomorphism phi to alpha, that gives me some ring element, I just multiply that by R. Okay, so via this definition, alpha scalar multiplying R is phi alpha times R. Okay, and now you can check that this satisfies all the axioms. Exercise, check that R satisfies the axioms of an algebra. Okay, so algebras, F algebras are really the same data as homomorphisms from F to the center. Okay, so why is one wanting to do this? Well, number one, algebras are ubiquitous, they occur a lot, and there are many interesting things one can do with algebras. For us, of course, the immediate motivation is the tensor product of algebras. Okay, and this is an important construction also. So suppose if I give you two F algebras, let R and S be F algebras. Again, F is the field that I fixed before. Then what can I do with it? Well, I can construct. So recall, F algebra means I've got a ring structure, or well, I have an abelian group structure. There is a multiplication, and there is a, or rather there is a ring structure and a vector space structure which are compatible with each other. Okay, now at the moment, forget the ring portion, let's only think of them as vector spaces over the field F. So I have R and S are both vector spaces over the field F. So I can, therefore modules over the field, I can talk about their tensor product. Okay, so consider the F vector space. F vector space R tensor F over the field F. Okay, so it's a vector space definitely, but I claim this vector space actually comes also with a ring structure. Okay, so how shall we define a ring structure on this? So recall R and S have multiplications, right? So let's define, we can define a ring structure. Okay, well, how can we do this? Well, again, let me just tell you what the final answer is in terms of the decomposable tensors. What we want is this, we want, so let's take an element, a simple tensor, of the form R1 tensor S1 and multiplying by R2 tensor S2. Okay, so well, I want it to be the following. I would like it to be I can multiply R1 and R2 in the ring R and S1 and S2 in the ring S. So look at R1 R2 tensor S1 S2. Okay, and this is what I want to be true for all R1 R2 in R, S1 S2 in S. But of course, you know, I can't, as always, I can't use this as my definition per se, because then I'll have to check well defined and so on. So what one does instead is, again, you know, you try to do it more abstractly using the universal property, so that you'll be guaranteed that there exists a well defined map like this. Okay, so let's try and give a proper definition. So again, I will leave most of the verifications as exercises. So let's sort of go back as far as we can. So instead of what is this a map from? This is, you know, the multiplication map is really, recall, it's a map from R tensor S cross R tensor S to R tensor S. So I mean, when I say ring structure, I mean a multiplication map. So let me define instead the following. From R cross S cross R cross S, I will define a map. Okay, so let's define a map F as follows. So what does F do? Well, it takes a tuple R1 S1 maps it to R1 R2 tensor S1. So I can always construct this map. Now the key point here is we need to sort of get the correct bilinearity and so on. So to do that, let's say the following. Let's fix R1 and S1. So you fix these two components. Think of it only as a map from R cross S to R tensor S. Okay. So this fixed map here. So let me call that map as F. So this overall map is called F, but this map which I get when I fix an R1 and S1. Okay. So this map, it sends R2 S2 to, let me give this a name. I'll call it F sub R1 S1. So I'm fixing R1 and S1 and I get a map like this. Okay. Now what properties does this map have? Okay. So the first claim is that this map is in fact F bilinear. So F sub R1 S1 is an F bilinear map. Okay, so again, check exercise. Okay, just plug in the, you know, change R1, change R2 and S2 and see what happens to the answer. Okay, so it's F bilinear, therefore by the universal property, there exists a unique map. Let's call it F tilde, but sub R1 S1, still depends on R1 and S1. This is now a map from R tensor S. Okay, and what does this map do? Well, it takes R2 tensor S2, maps it to R1 R2 tensor S2 S1 S2. Okay, so there exists, at least it's a well defined map like this. And what sort of map is this? This is an F linear map. Okay, now however this depends on an R1 and an S1 which we have fixed. So we now try and remove that dependence as follows. So look at the following. From R cross S, so for each pair R1 S1, I have now defined a map called F tilde R1 S1. Okay, now where does F tilde belong? Well, F tilde was a linear map. So it's in the space of all F linear homomorphisms from R tensor S to itself. Okay, if you go back and see, that's exactly what it does, right? It's a map from R tensor S to R tensor S, and it's an F linear map. So F tilde R1 S1 belongs here to the space of homomorphisms. Okay, so now you get a new map, should call it something else, psi maybe. Okay, and now claim again psi is also bilinear. Psi is F bilinear, which means when I change R1 and S1, I should see how F tilde R1 S1 changes. Okay, so again, proof exercise, check bilinearity. Okay, just a question of plugging in the definitions. Now again, therefore, by the universal property, there exists a unique psi tilde. This is now an F linear map. From where to where? From R tensor S to the space of F linear homomorphisms. Okay, such that this diagram commutes. Okay, so I should say this, such that what does it do? It takes R1 tensor S1 to F tilde of R1 S1. Okay, good, and that's more or less what we want finally. So now once you have a map like this, you can use this map to define your, this is exactly the map you want. This is the map psi tilde. So now we define a multiplication using this map. So psi tilde is well defined. That's what we finally wanted. Okay, that's the key here. So I should say there is a unique key point is this is a well defined map which does this. Okay, so now we use this map. Therefore, now we define a map from R tensor S. I'm going to define the multiplication map now. Okay, so how am I going to find the multiplication map? So I'm just going to say take for each R1 tensor S1 maybe one should just say, I want to do it more generally. I'm not just going to do it for the R1 and S1. So take a xi and an eta. Okay, xi is an element from R tensor S, eta is another element from R tensor S. How am I going to define their product? Okay, so I will define their product to be the following. It is just, so maybe I should say, okay, this goes to xi times eta, where I define xi times eta as follows. So what am I supposed to do? So I take this psi tilde map. So I know what psi tilde does to such elements, but in general it will take any xi to something, right? It will take it to some element xi tilde of xi. Okay, and that new element psi tilde of xi is now some endomorphism of R tensor S. So here's what I'll do. I'll first apply psi tilde to xi. Okay, the answer is now some homomorphism from R tensor S to itself. So I can evaluate it on an element of R tensor S. I evaluate it on eta, and what I will get will be some other element of R tensor S. Okay, so this is my definition finally. So once I get this map psi tilde, I can define multiplication as follows. It's psi tilde of xi evaluated on eta. Okay, but now observe that this definition has the following desirable property, that if xi and eta are both decomposable tensors, if this looks like this, then what's this new definition I have made? Well, it's just going to be, I evaluate psi tilde on this, evaluate the answer on this. Okay, but then we just saw psi tilde is nothing but F sub R1 S1 evaluated on R2 tensor S2. That by definition is exactly R1 R2 tensor S1. Okay, so that what it says is this is the correct definition. This is the formal way to define it so that it's well defined and so on. But on the decomposable tensors, it behaves the way we want it to behave, right? That's why we defined the map like that in the first place. Okay, good. So this is sort of this is the amount of work it took just to define the multiplication. But having done this, we still have to finally show it is an F algebra. So my final claim is that if I take R tensor S or F becomes in fact an F algebra with respect to this new multiplication I have defined, becomes an F algebra. Okay, in other words, the new multiplication that we just defined above, is compatible. So that third compatibility axiom is true with the scalar multiplication. Okay, so I am going to leave this also as an exercise. Okay, good. So what this finally does is to give you a powerful way of constructing new algebras from old ones. Okay, so I mean one can also you know if you take, instead of fields, algebras over fields, I can just take algebras over rings, commutative rings. So if I replace f by, say, the ring of integers, then a Z algebra is really the same thing as a ring. Okay, and this notion here is really like the notion of tensor products of rings. So given two rings, what you do is more or less follow the same sort of thing to construct a new ring whose operation is this interesting component-wise tensor, component-wise product, and then taking tensor. So I can define the tensor product of two rings, for instance, like this. Okay, so this is a rather powerful construction, and for example, in the category of rings, this is exactly the coproduct. Okay, good. So this is you can think of this as an application of this whole tensor products thing that we've been doing. It gives you a way of constructing products or co-products of rings, for example.